Hello everyone, welcome to the vectors video. So today we'll be talking about vectors, and we'll really be talking about vectors all semester. So this is a really important concept that we need to get familiar with. And it's basically because in physics we often talk about how things move, right? What forces are acting on one another. And vectors are kind of a way of describing not only the magnitude of things, but their direction. So we have two fundamental types of quantities we'll be discussing in class, scalars and vectors. So scalars are any physical quantity defined by a number of units. In other words, it's something that can be defined solely by its magnitude, how much of it is there, right? So the mass, like how much do you weigh, right? Or distance, how far is it from point A to point B? Speed, number of hamburgers, etc. Vectors are a quantity that has a magnitude, but it also has a direction. So something like your position, and displacement, how far you've moved, kind of depends on what direction you've moved as well if you want to accurately describe the displacement. Velocity, acceleration, force, these are all vectors where you need to have a direction specified in order to correctly describe it. And you might think right away, well, there's speed, and that's a scalar, and there's velocity, and that's a vector. So what's the difference there? Well, you're going to see in just a minute. We'll do a little example explaining the difference. So when we visualize vectors, we draw arrows. So that's really the simplest way to visualize a vector. And the length of the arrow typically tells you about the magnitude, right? The longer the arrow, the larger the magnitude. And the direction of the arrow, tells you the direction that the vector is pointing in. So you really need both a magnitude and a direction to describe the vector. And to illustrate that, I've written some vectors here, illustrated some vectors as arrows, vectors A, B, C, and D. And you can really use any letter you want in physics to describe something, as long as you're being consistent throughout the problem. So you'll get used to seeing any kind of letter, or sometimes Greek letters used to describe different variables, just a heads up. But anyways, this vector A and this vector D, you can see they're kind of pointing in roughly the same direction, but they have different magnitudes, right? They're different lengths. And vectors D, B, and C, they're all kind of similar in magnitude, but they have very different directions. So it goes to show you really need both in order to describe the vector. So a quick example of a vector. And this will help illustrate the difference between speed and velocity. So a ball travels upward with a speed of 4 meters per second. Okay, so we've just described a vector, and now we can write down what that looks like. So you notice we said speed here. We said that's a scalar. It's only having a magnitude of 4 meters per second, but we just specified the direction as well, up. So when we write down the vector, we write it down in a form in which we write down first, we write down the magnitude, 4 meters per second, and then we write down the direction second. Often we'll denote vectors as a variable with a little hat on top. It looks like a little mini arrow. And that's just shorthand to specify that the variable we're talking about is a vector. And sometimes we want to know, okay, we have a vector, and what's the magnitude of the vector? Sometimes we'll put little absolute value symbols around the vector and say the magnitude of this vector is its speed, 4 meters per second. So speed is like the magnitude of velocity. So often we'll be dealing with more than one vector at once, vector mayhem. And you'll need to be adding vectors, sometimes subtracting vectors. Next class, we'll talk about multiplying vectors even. But right now, let's just stick with adding vectors. There's two ways to do it. and they're equivalent. One is kind of the graphical method, where you draw the arrows out on top of each other. And the other is to add up the vectors algebraically. So let's say we have vectors m, n, and o. Vectors m, it has a magnitude of 3 meters and it's moving to the right. Vector n has a magnitude 1.5 meters, it's moving to the right. And vector o has a magnitude of 4 meters and it's moving to the left. So you can see we drew out what those look like here. So for the graphical method, we call it the tipped tail method. If we wanted to know what is m plus n. First, we would draw the vector m. And then at the very tip, at the end of vector m, we'd draw vector n. And draw it how we would normally draw it. So the sum of those two is the initial starting point and the final end point after you've added those vectors together. Okay, so that's what that looks like, and that makes sense, right? If we move 3 meters to the right, and then we move another 1.5 meters to the right, we end up going 4.5 meters to the right. What if we were to add vectors m and o? Remember, o is going 4 meters to the left. So to do that graphically, right, we draw out m, moving 3 meters to the right. We go from the tip of m and draw o, 4 meters to the left. And in the end, we've gone 1 meter to the left. Okay, so adding vectors, we've kind of got an idea of how to do that graphically. Subtracting vectors, we can pretty much do it the exact same way. So when we subtract vectors, we can kind of say it's kind of like the same as adding a negative vector. Right? Maybe that's a little counterintuitive or making it a little bit more complicated than it sounds. But let's say we have m minus n. That's the same as m plus negative n. And when we have negative n, it's kind of like it reverses the direction. So instead of moving 1.5 meters right, negative n would be moving 1.5 meters left. So we go 3 meters to the right, 1.5 meters left, and in the end, this is what the vector m minus n looks like. So some quick standard rules for vectors. They're commutative, which means a plus b is equal to b plus a. It doesn't matter what order you add the two in, which one's in front, it comes out to the same thing. And we have the property of being, it's called associative. Let's say you have 3 vectors, a, b, and c. It doesn't matter which of these two you add up. If you're adding all of them up, in the end, you're going to get the same result. So if you add a plus b and then add c, it's the same thing as if you first add b and c and then add a. So just to kind of nail the point home, if, for instance, a was moving 2 to the right, b was moving 4 to the right, so we'll say plus 4, and c is moving 5 to the left, right? It's like you add up 2 plus 4. We did that. We go 2 to the right. We go 4 to the right. And then we go back 5. And in the end, it's like the same as if we had gone forward 1, right? So it's the same exact result of this. At first, you had gone 4 to the right. And then we go back 5. And then we go forward 2, right? So you can see graphically, it looks a little bit different, right? We go forward 4, oopsies. forward 4, we go back 5, and then we go forward 2. In the end, we started here, and we end here, and our final position is the same. All right. So unit vectors are something we'll be using quite often, and it's a shorthand way of denoting vector direction. So what does a unit vector mean? It means it's a vector with a magnitude of 1. And we use it as a way to designate direction. So let's say we have a unit vector x, and it's moving in the x direction, and positive means it's moving to the right. Negative unit vector x means it's moving 1 to the left. So before we were talking about m being moving 3 to the right. Another way to write that now that we've introduced unit vectors, is just to say 3 meters in magnitude times this unit vector, right? And the unit vector is going 1 to the right, so that designates the direction. And n is 1.5 times the unit vector x. So if you were to do m minus n, now it kind of looks like 3 meters in the x minus 1.5 meters in the x, which is going to equal positive 1.5 meters times the unit vector x. So it's the same thing as writing 1.5 meters right. All right, so like I said, unit vectors, we kind of just use that as a shorthand of writing out the vector instead of writing out the word right or up or down. Okay, so 2D vectors. Now we're getting into it. Now we're leaving the one-dimensional plane and entering the two-dimensional plane. Sometimes you'll see vectors in 3D as well. Most of the physics we're going to do in this class is going to be just in 2 dimensions, but adding a third dimension isn't actually as complicated as it sounds, especially when just describing vectors. So with 2D vectors, we'll sometimes use the unit vectors I and j. This is what your textbook has. It's really the same. Some textbooks use the unit vectors x and y to denote horizontal and vertical. So it's really just a matter of convention. You can see both. Our textbook uses I and j, I being horizontal, j being vertical. So thinking about how can we use the same graphical vector method to add vectors in 2 dimensions. We still use the exact same method, tip to tail, right? So if we have vector A, which kind of goes up 2 and to the right 1, and vector B, which goes down 1 and to the right 1, you can first draw A, and when you get to the end of A, you draw B, and then that's what vector A plus B looks like. So let's say we have now vector C, which is going this way. Another way of writing it is to break it down by its components. So let's say we have this vector Cx, which goes the whole distance in the x direction that C did, except it's just parallel to the horizontal plane. And then we have Cy. You can see that if you first go along Cx and then you go along Cy, you get to the end of this vector C. So vector C is the same as Cx plus Cy. So that means we can denote vector C as the magnitude of Cx times the unit vector I, and the magnitude of Cy times the unit vector j. So that's how we can write down vectors in 2 dimensions. We'll write down a magnitude multiplied by unit vector I, and a magnitude multiplied by unit vector j. All right, so how can we numerically add vectors? We proved that you can use the exact same graphical method that you did in 1D as well as in 2D to add vectors. And you can pretty much do the same thing algebraically adding up vectors. So what you have to do is you break up each vector into components along orthogonal axes, and that's a fancy word for saying perpendicular, right? I and j are at a right angle, so they're perpendicular. And after you break up the vector along those orthogonal axes, you add up the like components. So what does that mean? Well, we'll often say like you add up both x components together and you add up both y components together, right? Things that are moving solely in the x direction are the x component, and the part of the vector that's moving solely in the y direction is the y component. All right, so let's say we have vector A, which is moving 3 to the right and 1 up, which we've written here. And we have vector B, which is moving 1 to the left and up 2, which we've written here. And so here you can see we've graphically added A plus B. But how would we do it algebraically? Right? So we take these, we add them up, 3i plus 1j, and then B, this is B, this is A. Right? You can see I've highlighted the I components in blue and the j components in red. And so when we say we add the like components, that means 3 is going to get added to -1, which gives us 2i, and 1 gets added to 2j, which gives us 3j. So we have A plus B equals 2i, 3j. And if you kind of look at this, that's the same as like, oh yeah, we went to the right 2 and we went up 3. So you can see that the numerical method and the graphical method give identical results. Often we'll see vectors expressed in angles. So you might be given the magnitude of a line, and then, for instance, you'll be given the angle between that line and the horizontal plane. You know, and you have to be careful with this because sometimes problems are tricky and you'll be given like this angle or this angle. So you have to be careful where your angle is defined from, right? But in this case, not always the case, but in this case, the angle is defined as between the vector and the horizontal plane. And so we can also still describe this vector A by its x components and y components, but now you can see right away that there's going to be a relationship between the ax, ay component and this angle theta, right? For instance, if this angle theta was smaller and the magnitude was the same, ax would be larger, right? And what if this angle was 90 degrees and we were going straight up? Then the ax component would be 0, right? Because you would still be along this line if theta was 90 degrees. Okay, so there's a relationship between theta, ax, and y, and you can actually see that the vector A and the ay and ax magnitudes, they form a right triangle. Right, a right triangle is where one of the sides has 90-degree angle. And the right triangle is our best friend. Make friends with a right triangle today. Have them be your bestie throughout the course. They'll see you through hard times. Because a lot of trigonometric functions pop up with right triangles that we're going to be using quite often. Right, sines, cosines, and tangents. Sine, cosine, tangent. We're going to see these a lot. So let's make a couple things clear. So if you were to take the sine of theta, that would be equal to AY over A. Because remember, sine theta, taking the sine of that angle, is equal to the opposite side of the triangle divided by the hypotenuse. Remember, the hypotenuse is always the side of the triangle that is opposite the 90-degree angle. All right? And in this case, AY is opposite the angle theta. All right? So sine theta is equal to AY over A. Cosine theta is equal to AX over the magnitude A. Because remember, cosine theta is always equal to the adjacent side, the magnitude of the adjacent side, meaning the side that's touching theta, divided by the hypotenuse. Okay, so we said earlier that A can be expressed as AY plus AX, in other words, AX times unit vector I, and AY times unit vector J. Well, what if we were to flip this around, right? We would know that AX, right? We know AX is equal to A times cosine theta, magnitude of A times cosine theta, right? We just take this equation, multiply A by both sides, right? A and A is going to cancel here, and then we have A cosine theta. All right, and then likewise, AY is equal to magnitude of A times sine theta. So we take those expressions and we substitute them in here and here, and we can say that the magnitude, the vector A is equal to the magnitude of A times cosine theta times unit vector I, plus the magnitude of A times sine theta times the unit vector J. The other beautiful thing about right triangles is we can use Pythagorean's theorem, which relates the size of the triangle, right? So the magnitude of A, the hypotenuse squared, is equal to one side squared plus the other side squared, AX squared plus AY squared. And so if we take the square root of both sides, the square root cancels with the square, and we just have the magnitude of A equals the square root of AX squared plus AY squared. Okay, the last trigonometric function we'll be using is called tangent. Tangent of theta is going to equal the magnitude of the side that is opposite divided by the side that is adjacent. So what's opposite? AY, and what's adjacent? AX. So it's going to equal AY over AX. So you'll be using these trigonometric functions a lot, and I know you've probably used them before, but anybody can mix them up. They're really easy to mix up. So I would encourage you to, if you probably have heard this phrase, SOHCAHTOA, right? So sine stands for opposite over hypotenuse. Cosine stands for adjacent over hypotenuse, and tan stands for opposite over adjacent. So anytime you're looking at a problem in a homework set or on an assessment, always remember to soak your TOAs and double check that you're using the right trigonometric function. All right, so sometimes, you might be given the sides of a triangle, right? If I told you this vector has an x component of 3 and a y component of 4, I might ask you to solve for this angle, right? So we said earlier that tan theta is equal to AY over AX. So taking the inverse tangent of both sides, you have theta is going to be equal to arctan of ay over ax. So you could solve for theta this way. Okay. So we've gotten a lot of notation that I've thrown at you. And now it's time to put it to practice with a couple of practice problems here. All right, so this problem is a word problem. And you're going to see we're going to have to add some vectors here. So you walk south for 1 mile and then east for 1 mile. How far must you walk and in what direction to get back to your starting point? All right, so first thing to note is that, we're in a two-dimensional kind of problem and we need a coordinate system. So we're going to say east is positive, north is positive in the up direction, west is negative, and south is negative. And we'll say that, we're going to define an angle theta that starts going in the east direction, so 90 degrees would be north, 180 degrees would be west, right? 270 degrees would be going to the south. All right. First things first, whenever we get a word problem in physics, the first thing to always do, and pretty much without fail, this is the best way to start a problem, is really to draw a picture. Okay? So let's draw a picture and try and graphically draw these vectors to get a sense of what's going on. So let's have our starting point be here. And we'll define this point as 0, 0. All right, and so we're going to walk 3 miles, 1 mile south. All right, and now we're going to walk 3 miles east. Okay, and what is the question asking? It's asking, how far must you walk and in what direction to get back to your starting point? So it's asking, what is this vector? Okay, interesting. So you could probably see right away we can answer the first question really easily. How far must you walk? All right, what do we see here? This was a fairly simple problem where we first just walked south and then we walked east, so we know these two vectors, they're at a right angle, right? Which means we can use Pythagorean's theorem. So let's label this h. Why not? H for hypotenuse. We can use Pythagorean's theorem. H squared equals 1 mile squared plus 3 miles squared. All right, and so h is going to equal the square root of 1 mile squared plus 9 miles squared, right? So I already carried the square through. 3 squared is 9. And so h is going to be the square root of 10 miles squared. And I don't have my calculator on me, but that's around 3.34, right? Okay, so we know that's how far we have to walk, but in what direction? So we're going to want to put it in this convention, right? So 90 degrees would be walking north. So what direction are we walking? So actually what we want to know is, we said this direction is east, right? And 0 degrees is our east, right? 90 degrees is north. So what we really want to know is, what is this angle? Okay, and maybe we're not sure. We're not sure what that angle is. But I bet you could tell me what this angle is. All right, we can use those handy dandy trigonometric functions that we just learned about. All right, so if we labeled this guy theta, all right, let's use that handy dandy trigonometric function we just learned. 3 and 1, so let's say we wanted to know tan theta. What's that going to be equal to? SOHCAHTOA, opposite over adjacent. It's going to be equal to 1 mile over 3 miles. Units here cancel out. All right, it's going to be equal to 1/3. So theta, that angle theta is going to be equal to the inverse tan of 1/3. All right, and what the problem is specifically asking is what direction in terms of this coordinate system. So really it's asking, what is this angle theta 2? Hopefully you might remember, how many degrees are there in a circle? 360, right? And if you cut a circle in half, how many degrees are on this side of a circle? 180, right? So theta 2 is going to be equal to 180 degrees minus theta, or theta 1. Let's call this theta 1. Okay, so we've pretty much solved it. You know, if you want to actually calculate what is the arctan of 1/3, and then convert that, be sure to convert it into degrees and not to do a problem where you mix degrees and radians together. That's a common problem. All right, so we've done it. We've figured out how far we were going to walk using Pythagorean's theorem, and we figured out what direction we were going to walk using this tangent. Okay, on to one more example. You fly a plane with a velocity of 100 kilometers an hour at an angle of 30 degrees above the horizon. You then fly with a velocity of 150 kilometers per hour parallel to the ground. What is your total velocity vector? Okay, so what did we say was the first thing that you're supposed to do when you encounter a problem in physics? Draw a picture. So now we define our starting point as 0, 0. All right, we'll draw the ground here. And then we'll draw a very nice airplane, or attempt to. All right. We are going V1 is equal to 100 kilometers per hour at an angle of 30 degrees. And then we move with V2 is going to be equal to 150 kilometers per hour. All right, so we can, add these graphically, no problem, right? And we, in fact, already did. I kind of just did add them graphically. So it's asking, what is this? And can we write that out numerically, right? So first things first is maybe we want to write out the x and y components of V1. All right, so let's draw V1 by itself. 30 degrees. So this is V1. So we want to know what is V1x and what is V1y. Okay, so we know that Vx, or V1x, is going to be equal to the magnitude of V times cosine And the magnitude of Vy kind of equal to magnitude of V times sine theta. It's just trigonometry. Once you get practice at it, it'll just be like breathing. All right. Now, if we were to write this out in vector form, right, it's V naught sine theta. Oopsies. Made a mistake. Just a little one. Times the unit vector I plus V naught times sine theta times the unit vector J. Right? This makes sense. And if we want, we can go ahead and plug in these numbers, right? Okay, so it turns out that cosine of theta, which is 30 degrees, is equal to 0.86. So we have the magnitude V1, 100 kilometers times 0.86, and then the magnitude 100 kilometers times sine theta, which is 0.5. So we can write out V1 is 0.86 kilometers per hour times unit vector I plus 50 kilometers per hour times unit vector J. In other words, our velocity is kind of in the x direction at 86.6 kilometers per hour and in the y direction at 50 kilometers per hour. And what is V2? Right? V2 is moving just horizontally 150 kilometers per hour, so it has a horizontal component and has 0 vertical component. So if we were to add V1 plus V2 to get V3, remember we add the like components, we add the I components together, and there's only one J component. So our final answer would be our total velocity vector is 236.6 kilometers per hour times I plus 50 kilometers per hour times the unit vector J. All right, so hopefully you've learned some from those examples, and take a look at the slides on the next module for some more vector examples, and see you in class.